Oh, what a beautiful view! Conserving momentum is just one of those things you always do when you see a collision happen. In this podcast, we've got a couple of examples of collisions, and we want to see how momentum is conserved in these different situations. In the first collision, we've got ball A striking ball B, which is initially at rest, and then they just continue on moving afterwards. In any time you conserve momentum, you write that the initial momentum is equal to the final momentum. The next thing you do before you try to write any sort of equation is ask yourself, what has momentum before and after the collision? The initial momentum is all in ball A. Since both balls have momentum after the collision, because both balls have mass and both balls have velocity, we would write ball A plus ball B. This is always going to be a plus sign because we sum the momentum. It's always a summation. If a momentum happens to be in the opposite direction, we can add that negative sign in at the velocity stage. We'll see that in a second example. But right now, this correctly identifies what has momentum both before and after the collision. Anything that has momentum then gets a mass times velocity statement. So the mass of A and the velocity is given as 4 equals the mass of A times 2, as a subscript A there, plus MB VB. With these conservation of momentum problems, there's so many masses and velocities, it's important to always use some subscripts. And we could even put F right here for the final velocity of B. If we had both the masses, we could go ahead and fill those in and solve for what was the final velocity of B. But the focus of this podcast really is just setting up your equations. Doing the algebra is going to be left up to you guys. What you can see is we stated that the initial momentum equals the final momentum. Then we used the second step to list the things that had momentum. And then anything that has momentum, we enter its mass times velocity for its momentum. And you should wind up with an equation that's solvable. In this situation, what we want to look at is we've got the two balls moving towards each other, and then the balls moving away from each other. Since I've given you all 4 velocities here, chances are a problem like this would ask for one of the masses. Again, we're not trying to solve problems in this podcast so much as we are looking at how to properly set up a conservation of momentum equation. We'll write that initial momentum equals the final momentum. Initially, both balls have momentum. And after the collision, both balls have momentum. Having this initial statement gives us headings kind of for initial and final. Well, this is where we need to choose a positive direction. Let's let to the right be positive. Well, that would mean we'd have MA times 4 plus MB times negative 4. And over here, we'd have MA. Now look at this. We've got to stick with our frame of reference. So as we look at the diagram, you can see how important it is to have a diagram now to guide us. If we've established that right is positive, then this would be a negative 2, and then MB positive 2. Now again, in this type of problem, chances are if we gave you all of the velocities, we need to give you one of the masses so you can solve for the other mass. But what we want to focus on here is establishing your frame of reference and then making sure you follow it as you enter the different velocities. We'll always add the two momentums because we're summing the momentum, but when we've got a velocity that goes the opposite direction as the way we described was positive, we've got to enter it as a negative there. Those are basic collisions. There's a couple of special types of collisions you can also look at. Maybe as we roll the balls towards each other, they were magnetic and they stuck together, and then they slid off together, of course, on a nice, happy, frictionless physics surface that exists only in physics problems. But who needs friction complicating things? Well, it's still a collision, so we can still say that the initial momentum equals the final momentum. And according to the diagram here, B is just sitting here minding its own business before it gets hit by A. So ball A is the only thing that has momentum to begin with. This type of collision where they stick together, that's called completely inelastic. A completely inelastic collision is where the two items that are colliding stick together and travel off together in the end. A just regular inelastic collision is pretty much the bulk of all collisions, where momentum is conserved but energy isn't. If you think about when things collide, you hear a lot of sound. There's deformation. The things colliding get deformed. All these are ways for energy to leave the system. A completely elastic collision is one where energy is conserved as well as momentum. Those are pretty rare. Collisions between particles in a gas in a closed container, those are approximated to be elastic collisions. So a question has to say a collision is completely elastic in order for it to be considered elastic. Otherwise, energy is not necessarily conserved in the system of just the two objects. Well, once again, completely inelastic is when they collide and stick together. And what we do is we treat that now as all one object. So we'll say the balls together, maybe put brackets around them to show that it's all one object, as the object has momentum here. So again, we do the mass of A times 4. Again, letting right be our positive direction here. And you can see that this whole problem happens to the right. So sometimes you might not even explicitly specify this, but it's always a good thing to think about. So mass of A times 4. Now our mass term, we've got to use some parentheses here because this object is the mass of A plus the mass of B. But there's only one velocity. I'll just put VF there. There's only one velocity because they move off together. And so you could be given the final velocity and one of the masses and solve for the other mass, or you could be given both masses and have to solve for the final velocity. There's all sorts of things you can solve for. But the setup is, as always, look at what has momentum before, look at what has momentum afterwards, and then do a mass times velocity for anything that has momentum. The last type of specialty problem is called a recoil problem. We have two items that start together at rest, and then some kind of internal force, like an explosion or a spring, or maybe it's two figure skaters pushing off of each other. Who knows? But you start with two things stationary that push off of each other and take off. And in this setup here, maybe we're trying to find the final velocity of A. What you do here is you still say, you've got to recognize that this is recoil from the fact that they start together and they push off apart. And as we look at our before and afters, our initials and finals, we see that in the beginning, neither object has momentum. So this beginning term is 0. And so we'd have ball A plus ball B having momentum afterwards. Again, this is a plus sign here. If we stick with right being positive, we would say that MA times VA. Now since VA, the velocity of A, is unknown, we don't instantly stick in the negative sign. We'll put MB times a positive 2 here equals 0. Now by the time the algebra comes out here with a positive velocity here, unknown velocity here, you'll get a negative answer for your velocity, which is what you expect if to the right is positive and A flies off to the left. So the negative is going to take care of itself there. We'll just leave it in as an unknown and let the algebra bring the negative to us. So in a recoil situation, your starting momentum is 0. And what happens is these two momenta wind up being equal but opposite. Now, depending on the masses and velocities, the exact masses and velocities may be different, but the total momentum of A and the total momentum of B, that's what's equal and opposite in that situation. So we looked at 4 situations in which we conserve momentum with collisions, completely inelastic collisions, and recoil situations. And in each case we conserve momentum, ask ourselves what has momentum, and then anything that has momentum gets an MV. You should be finished up with the problem with only one variable by the time you substitute in all your given information.